This video is on one example of Galois correspondence. And the Galois correspondence will be an effective way of describing subfields in a given field. So the field in question is the cyclotomic field of conductor 7, the result of attaching all complex roots of 1 of degree 7 to the rationals. That is as good as attaching just one of them, say e to the 2 pi I over 7 to the rationals, and that can be seen as the extension of rationals, and the answer will be a complete description of all subfields. And writing rationals at the bottom, and they will be subfields of this, so this will be at the top. Everything which will be in between. Any subfield will contain rational numbers. Rational numbers form a prime subfield, which is contained in any field of characteristic 0. So the Galois correspondence requires a good knowledge of the group of symmetries of this, and we have it. The automorphism group of this field over the rationals, or just as it is, it's the same thing. Rational numbers are fixed anyway. It is labeled in a very convenient way, but by integers mod 7 under multiplication, the multiplicative group of this finite field of 7 elements. And as a finite field, this multiplicative group has to be cyclic. So that is just a general knowledge. It has to be isomorphic to the additive group of integers mod 7. So this knowledge gives us a full control over the story of subgroups. And the Galois correspondence requires, it says that the picture of subfields is a replica of the picture of subgroups, but we have to flip it upside down. So at the top we'll have the trivial group, at the bottom we will have the full group of integers mod 7 under multiplication. And that, according to this isomorphism, is the same as a picture of subgroups of the additive group of integers mod 6, also flipped. And we know this lattice of subgroups very well. These subgroups are labeled by divisors of 6, so the lattice flipped is the lattice of divisors. So we have one divisor, which is 2, and the other, which is 3. They are the only proper divisors. And then another piece of information which is going to be useful for our computation is these indices, and this index is just the order of this group, which is the order of 2 as an element of this cyclic group for the 6. And 2 will have to be taken 3 times to get 0, so this is a cyclic group for the 3. And this is a cyclic group for the 2. 3 has additive order 2 mod 6, and that has to be replicated across this rhombus. So that picture is transported along this isomorphism into the picture of multiplicative subgroups. So we'll have a group of order, a subgroup, cyclic subgroup of order 3, a cyclic subgroup of order 2, and they will have to have these indices. So the cyclic subgroup of order 2 is easy. It's just -1 cyclic subgroup generated by -1. And -1 mod 7 is the same as 6. So the elements in these are just identity and the class of -1, which is the same as 6. So here we have to find an element for the 3. Well, we can of course just construct an isomorphism and do the transition from this lattice to that lattice, but it's easier to just find an element of order 3 and hence find its cyclic subgroup. So let's just look through elements in this group and see which one has order 3 first. And the first in the list is 1, of course, but 1 is the identity element, so its order is 1. So what is the order of 2? Multiplicative order of 2 modulo 7. It's the smallest power of 2, which is congruent to 1 mod 7. And it's not square, because square is just 4. It must be the cube. The cube is 8, and it is 1 plus 7. So the multiplicative order of 2 is just what we want, is 3. So this answer is just the cyclic group generated by the class of 2 mod 7. And explicitly it consists of 3 elements: the class of 1 mod 7, the class of 2 mod 7, and the class of 2 squared, which is the class of 4 mod 7. So this is the complete lattice of subgroups of this symmetry group, and then the identification between the labels and actual symmetries is as follows. So the class mod 7 corresponds to symmetry. I'll call it sigma, this is the label K. And the definition of this symmetry is by its effect on the generator of the field on this epsilon. And the effect is just raising epsilon to the kth power. So now we are ready to run the Galois correspondence, and we already can write a placeholder for the intermediate fields. We just have 2 such. One will be of degree 2, a quadratic extension of rationals. The other will be of degree 3 of the rationals, and they will be of index 3 and 2 in the cyclotomic field. And say this one will be the subfield of everything fixed by these symmetries here. So that will be the subfield fixed by the symmetry with the label -1. So I'm just keeping the generator because everything else comes to the right. Well, we actually have just the trivial elements on top of the generator, so that is obvious that everything just fixed by this symmetry is fixed by the whole group. But it is also true for this cyclic group to compute its subfield of invariance. We just need to take one of the generators, either 2 or 4, I'll take 2, and look at everything which is fixed by the symmetry, and everything which is fixed by this symmetry will be also fixed by the symmetry with the label 4, because the symmetry with the label 4 is just the square, the composite of this with itself. So what is left is like to look inside the subfields and see which numbers are in them. I will start with this degree 3 extension of the rationals. And I will be using one little algebraic trick, how to compute elements of the subfield, how to compute elements which are fixed by, say, a given symmetry or a given subgroup of symmetries. The trick is to average. The trick is the same as in writing relative traces, which we did before. And this is this averaging, additive averaging. So I claim that this sum over all elements of the cyclic subgroup will be fixed by the cyclic subgroup, will be fixed by the symmetry. Yeah, that was checked before, but it's really easy. If you apply the sigma in with -1 label to this, you will just reshuffle the order of summands but not change the sum. So what is it exactly? It's the sum of epsilon and epsilon inverse. And let's look at this symmetry a bit more closely. This is a symmetry which takes epsilon to its inverse, which takes any power of epsilon to the inverse of that power. And it's the same as the effect of complex conjugation. So this thing is a complex conjugate of whatever we apply it to. So this is a sum of a complex number in its complex conjugate. And as such, it must be real. And looking back at what the number is, this is this root of 1, this sum of this number and its complex conjugate is twice the real part. And the real part of this number is cos of 2 pi over 7. So that is this generator now, I claim, of my degree 3 extension, because this number is not rational, so it has to be of degree 3. The only degree it can have is the divisor of 3. Let me call it for short alpha. And what I will be now computing is its minimal polynomial. So we'll need to see what is the smallest linear relation with rational coefficients among powers of alpha. Well, I will start with something which I know, the smallest relation among powers of epsilon, and that is the cyclotomic polynomial number 7. And that is the sum, 7 is a prime, so that is the sum of all powers from 6 down to the 0th power of epsilon. The square and the first power and 1, and it's all equal to 0. And I will use it to find the smallest, the minimal polynomial of alpha. But first I will rewrite it slightly by changing large powers of epsilon into negative versions. I know that the 7th power of epsilon is 1, so the 6th power is negative first. And the 5th power in the same way is negative squared. And the 4th power is negative cubed. And then I will keep what I had. And now I have epsilon inverse and epsilon, which is my alpha. And I also have epsilon negative squared and epsilon negative cube and epsilon cube together. They're not quite powers of alpha, but they're very close to them. So let's see what the square of alpha is. If we just write it as a square of epsilon plus epsilon inverse and use the binomial formula, we'll have the sum of squares and then twice the product of the two, and that is just 1, so we have extra 2. Similarly for the cube, we use the binomial formula to get the cube and then the negative 3rd power, and then with coefficient 3 we will have the square of 1 and the other in the product, and each such product is just either epsilon or epsilon inverse. So what I have for this sum is that it is alpha squared without 2, and what I have for this sum of cubes, it is alpha cubed without 3 alpha. And that's what I will use in rewriting the sum here. So that, well, I'll start with 1, but then I have this together giving me a copy of alpha, and I have this together, these 2 giving me alpha squared but without 2, and then I have this together, and that is alpha cubed but without 3 alpha. And on simplifying it, I'll have alpha cubed and then 1 copy of alpha squared, and then negative 3 copies of alpha and copy of alpha give me negative 2 copies of alpha, and then I have negative 2 and 1, which will come down to negative 1. So that is equal to 0 according to this chain, and that is the smallest polynomial on alpha. Again, this is an irreducible polynomial. It doesn't have any roots in rational numbers. In integers it doesn't have any roots because they will have to be plus or minus 1, and none of them will. So I can say that abstractly as a ring, this field can be described as the quotient of the polynomials with rational coefficients by the ideal generated by this cubic t cubed plus t squared minus 2t minus 1. If you compute the discriminant of this polynomial, you'll have a little surprise. It will be the square of 7, the same 7. It will be 49, and being a square, it means that the symmetry group of this extension is the alternating group A3, the cyclic group for the 3. Okay, now let me describe the second of my subfields. It is a quadratic, so the description will be particularly nice. Any quadratic extension of rationals is generated by some square root. So I just need to find what is the square root. And the square root I can see if I see any generator and then look at the discriminant of its minimal polynomial. So let me start with some generator which I will get by taking epsilon and doing the averaging along the cyclic subgroup of this element along these labels. So I'll have epsilon, and then I'll have sigma 2 applied to epsilon, and I have sigma 2 twice, sigma 4 applied to epsilon. Well, sigma 2 squared, really. But then I'll have the sum of powers of epsilon in this way. And that I'll just call for short beta. and I will be trying to find the minimal polynomial for this beta using basically the same technique, starting with the minimal polynomial for epsilon and massaging it in some algebraic way. But really I will just do it head on. I will start by computing the square of beta. So what is the square of beta? And it is the square of the sum. And using trinomial formula we can write it as the sum of squares. So epsilon to the 4th power squared is epsilon to the 8th power, but 8 mod 7 is 1, so I just have epsilon. And then with coefficient 2 I have 3 products of different summands. So I'll have epsilon with epsilon squared, which gives me epsilon cubed. I have epsilon with epsilon to the 4th, which gives me epsilon 5th. And then I have the product of these two, which is epsilon 6th. So that is just the trinomial formula. But now I'm going to use this sum. So what does it say about my triple sums? If this is beta, then this other two is added to beta and to 1 give me 0. So I can say that this is what? This is something, if I add beta and 1 I will get 0, so this is negative 1 and negative beta. Right? And this is actual beta itself. So now I have my quadratic relation. I have beta, I have with coefficient 2, I'll take minus out. I'll have 1 plus beta. So if I let the dust settle, I will have a beta without 2 copies of beta, so negative beta, and then I'll have negative 2. And put together on one side as a relation, as a polynomial relation, I'll have this. And that's what my quadratic here is, but I can do one more pushing and write it in even better way as a result of attaching a square root to the rationals. So what is the square root? This is this discriminant of the polynomial. Well, we can see it explicitly finding beta, but it also involves computing the discriminant first. So the discriminant is the square of this coefficient, which is 1, and then without 4 times this coefficient, which is 8. And it's negative 7. And so this is my field here, this is my quadratic extension here. And this is the complete story of all intermediate subfields of that given cyclotomic field. We just have 2 interesting non-trivial, one is quadratic, one is cubic. And I will stop here. See you later.